of this concept. You know, in classical electromagnetic theory, an electric field, imagine we have an electric field which is propagating along the z direction. So I can write down the electric field E of x, y, z, and let me write it as E of r as E0 of r into e to the power I kz minus omega. This will be solution of a wave equation in charge free region. It's called a plane wave. So E0 is an amplitude. Now if it is propagating along the z direction, the electric field will have components along x and y. There won't be any component along the z direction. So we can write down this E0 as a vector Ex and Ey. Now Ex and Ey can be, it's a field. What do you mean by a field? It will have some value at every point in space and perhaps in time. So let us look at a particular time and get rid of this dependence on time. Or if you have a locus of points at a particular time in space, this is actually a complex number. You can have a complex number. Ex can be a complex number, Ey can be a complex number at a particular point in space. So if you look at set of all Ex, Ey that you can have, that will become a vector space of two-dimensional vector space on complex field. So this in general belongs to C. There's a complex vector space of. Now you know that depending on what are these values, you can have the state of polarization. Suppose if this is not there, if Ey is equal to 0, only Ex is there. We say it's a plane polarized or linearly polarized. You can define that as a horizontal polarization. But if this is 0, this is 1, this is only there, then you can call this as a vertical polarization. But if both are there, 1 by root 2 times this and 1 by root 2 times this, then you can call that as a 45 degrees polarization. Similarly, with the minus sign, you can talk about minus 45 degrees polarization. So you can see the polarization state of an electromagnetic beam can be represented as a vector in the complex Hilbert space. So correspondingly, you can say if I define horizontal polarization, that corresponds to 1, 0. Vertical polarization, that corresponds to 0, 1. Diagonal polarization corresponds to 1 by root 2 times 1, 1. And minus diagonal polarization corresponds to 1 by root 2 times 1 minus. Now, from polarization optics, tell me what this corresponds to. 1i. That means Ex is phase shifted from Ey by 90 degrees. It's circularly polarization. So you can say this is right circularly polarized, and then you have left circularly polarized as 1 over root 2 as 1 minus. Actually, in electromagnetic theory, these vectors are called Jones vectors. Jones vectors. Jones vectors describe the state of polarization. Now, any alpha and beta, okay, so you can call this as any alpha and beta such that, let me call this as E. Let me define this as a set omega, where alpha and beta, such that alpha square plus beta square is equal to 1. Alpha beta such that 1 alpha square plus beta square is equal to 1 is a general elliptical polarization state. A general elliptical polarization state. You know, this can be written as alpha times horizontal plus beta times. So a general state can be written as alpha times horizontal plus beta times vertical. Correct? And I can have a very nice interpretation of this one if I write a general state, let's call this as A and B here. 1 is square is equal to 1. So let me call this alpha. A general state as I will parameterize in such a way because of this condition mod A square plus mod B square is equal to 1. I will write it that as cos theta by 2 times horizontal polarization plus sin theta by 2 into e to the power I 5 times vertical polarization. So if I consider horizontal and vertical polarizations as the basis for my C2, then I can write the general polarization state as cos theta by 2 plus sin theta by 2 into e to the I5 with horizontal and vertical polarization. Now realize that mod square of this plus mod square of this is equal to 1 by construction. But this construction allows me to have a geometrical interpretation of this polarization states. So you know, if I consider a unit sphere, and then the given theta and phi as a part of spherical polar coordinates will define a point on the sphere. So I give different values of theta and phi, I give different states, and every state can be located on the surface of the sphere. Correct? So that way, all polarization states are mapped onto the points on the sphere. Okay? In polarization optics, this is called point sphere. For example, if you want to represent horizontal polarization state, you know theta equal to 0, phi is equal to 0, so this will be horizontal polarization state. Diametrically opposite will be vertical polarization state, and this will be diagonal, and opposite will be minus diagonal. And along this line, you have all circular polarization states, and any point is an elliptical polarization. So you see that all polarization states can be put on as points on the point sphere.
So what is the significance of theta and phi?
That is only to geometrically locate these states. No, there is no physical. See, when I have this coefficients mod A and mod B, I can parameterize them in the way I like. So this is a particular way of parameterization, where I can identify these theta and phi parameters as azimuthal and angles of the spherical polar coordinates. So neatly I can have a geometrical visualization of the polarization states. So you know, there is something called, for example, you know, one physical effect. If you start from this point, okay, so you go on changing the polarization state of light, and then you take a loop and come back here. What do we expect? We expect physics should not change, right? I'm taking a point and then going around in the sphere. That means I'm changing the polarization state of light. You can change the polarization state of light by putting up polarizers, analyzers, etc. And then I take a deep U-turn come back there in a loop, I expect I should have the same state of polarization, but it turns out that there is a phase that is acquired by the electromagnetic field when you are going around a closed path. So this is called Pancharatnam phase. And Pancharatnam phase, much later in quantum mechanics, this was discovered by Michael Berry. It is called Berry phase. So Berry phase is the phase acquired by this loop. In fact, we have done this experiment in our optics lab at Pardon University. Since it acquires a phase, we can actually combine the beam that comes back after one loop and then the beam that originally is there through some beam splitters, and you can observe there is an interference because of the acquired phase. So by observing the interference, you can show that there is a phase that is acquired by detouring in some So this is called Berry phase. And just to conclude this application now, let me say that if you have a polarized light, I keep some medium, some kind of a scattering medium, and I know if the light scatters off, then the light that comes out may not be completely polarized. So there is some depolarizing effect that will be there. There are several effects. The polarization plane may be rotated, and some birefringence may happen, or sometimes there is a depolarization. So if depolarization happens, the light beam that comes out is not completely polarized, but it is not totally unpolarized also. The state of this partially polarized light have to be represented by some point within this sphere. So in statistical mechanics, what we are calling as mixed state is analogous to this partially polarized state. Pure states are analogous to completely polarized states of this light beam. So this is an exact analogy of classical electrodynamics and quantum states. So mixed states in quantum mechanics are like so mixed states are similar to partially polarized. Similar to state of partially polarized. Now in quantum mechanics, like spin system, the algebra is exactly the same. But the spin system or any qubit, nowadays in quantum information we call it as a qubit. If you take a quantum two-level system, the same sphere in this quantum mechanics universe is called a block sphere. And mixed states are the interior of this qubit states are and a general if we label zero for the basis vectors 1, 0 and 1 for the basis vectors 0, 1, we label that a general pure state. A general pure state is given by an alpha which is equal to cos theta by 2, 0 plus sin theta by 2 e to the high pi 1. And a general mixed state is defined by rho is equal to half I identity plus a vector x dot sigma, where sigma is sigma x I cap sigma y j cap sigma z. Then sigma x, sigma y, sigma z are Pauli lines. And sigma z is equal to 1, 0, 0. This x is an arbitrary vector and x is equal to x1I plus x2j plus x2. And if you ask the question that this rho has to be positive, okay, so rho has to be positive, rho is positive if and only if modulus of x is less than or equal to 1. You can show that condition. If rho has to be positive, modulus x is less than or equal to 1. And if modulus x is equal to 1, if modulus of x is equal to 1, then it is a pure state. That means all pure states will be on the surface. So you can write down this x, y, x1, x2, x3 as the coordinates of the point on the surface of at the state. If x1 square plus x2 square plus x3 square is equal to 1, we will be on the surface, you will have all pure states. If it is less than 1, you will have mixed states. So that is the reason why I said that within the Poincare sphere is partially polarized. States are partially polarized like okay.
Is there any algebraic similarity to Dirac equation?
No, right now there is no similarity with the Dirac equation because this is a general state. Okay, so Dirac equation is based on another rule, but let me come back to it later. At this moment there is no similarity.
They are fighting that operator.
That is because